architecturally, it's still a finite state machine. It still has a structure where there's memory over here, and then there's
nothing really more than logic up here to say if I'm in a certain state, then go through a bunch of logic to determine what the next state's going to be, and then when the clock goes off, make the current state in that next state, and change it to the current situation. And then that will in turn determine what the next state is when the clock goes off, and that's the thing. Now this is a very, sorry. The clock is a wire
that connects to all of these little triangles over here, these arrows that are here, and gives the impulse to all these things at exactly the same time, saying, do it now. Okay? And as a result, the machine transits from the current instruction to the next one. And then that instruction does its work here, and all that data percolates through, and then the clock ends.
Most of our time talking about today is how do you determine how long of a time to lose in between the pulses of the clock. And as you know, for chip manufacturers, that number, how many megahertz the chip runs at, it says, how fast, how often you can clock it in a second of time, matters a great deal. And so you have a gigahertz, for instance.
Is the current sort of level that chips are at, or 1.2, 1.4, even 1.5. So the general structure of any finite state machine, including the computer that we've been looking at, the beta, including every computer that's been made that is a digital one, looks something like this. There are some kind of inputs to the system. The computer we've drawn so far, I haven't shown you any of the inputs, but I've kind of hinted that there may be a keyboard hooked up, or a mouse, or a network interface. But in general, machines have inputs that come from the outside world. They also have outputs that go to the outside world. And again, in our computer, we haven't talked about where the output shows up. It might show up on the screen, for instance. Or if it was a different sort of finite state machine controlling an arm, it may make the arm move. All sorts of things like that. And what we have talked about, however, is this cycle on the inside. There's an idea that the machine is in a current state. In other words, how it sits right now. Described by a truth table, that current state is the next state should be. The current state is from the outside might be, for instance.
Can we try general B?
Oh, are we getting interference? There we go. How's that? Testing 1, 2, 3. Same thing? It must be from the work they're doing or something. Okay, well. Sorry. There, right? If I stand a little bit closer in, does that help? No, okay. Oh, it's really that. Now, I know that this is a little bit difficult to grasp all at first, so let's do a machine which we will never see at Ars Digita, but which actually does exist in the outside world. Free. But, so, that's cool. Actually, before I was 15 cents. And, let's assume that we want to build a very simple finite state machine, which is a Coke machine, and it only accepts either nickels or dimes, and thus the FSM has the input. One of the inputs to the FSM is a thing saying that it's gotten a nickel. Another input is a thing saying it's gotten a dime. And what that means is that there will be a 1 that sort of pulses high and then goes back down when you put a nickel into the machine, or a 1 that goes up and then back down when you put a dime into the machine. What are the other inputs that this thing might have? This is a very simple machine. It's only going to have one button, which is going to say, give me a Coke. Okay? It's sort of made for nerds here. And then finally, it will have another one saying, whoops, I've changed my mind, and it has, give me my money back. And those inputs are all going to be combined. So here's these 4 bits. And they're going to go into our logic, and I'm going to call this combinational logic, like I did in the last slide. And what that means is that it's just logic that's described by a truth table. And this is input. And we're going to have a memory that's going to be the state memory. And that state memory will put out, and I don't know how many bits it's going to take yet, but it's going to put out what we're going to call the current state. And what the machine's job is going to be to remember the current state, consider the input, and on the basis of those 2 pieces of data, the logic table will tell us if I'm in this state and the input is such and such, what should the next state be? Okay, so for instance, if there is a state for giving all the money back, when the return line comes in, it may say go to that state. Okay, and then this state memory in turn will be triggered by a clock signal that goes up and down, and we're going to say during the upward transitions from 0 to 1 of the clock signal over here is going to be when we're going to make the transition from one state to the next. And then of course, since it's a Coke machine, it needs some output, and it's going to have the following outputs. It's going to have one saying drop a Coke, right? Another one that says give back 5 cents, return 0.05. Another one saying return a dime, and another one saying return 15 cents. Now, we're not going to make the machine very complex. In other words, we won't have it actually count out nickels and dimes. We'll just assume that there's other logic beyond here that when it's told to return 15 cents, it figures out how to give a nickel and a dime, okay? So there will be 4 outputs as well coming out of this thing. And so this is the structure of what's going to be inside of our little controller for the Coke machine. Now, how do we actually describe how this thing works? Well, I happen to know the answer to this thing, that in fact, it only takes 4 states to do this. So let's actually draw the 4 states here. 1, 2, 3, 4. Okay, now, when we first plug the machine in and turn it on, it needs to be in some kind of a starting state. Okay, the machine is first powered on, and hopefully that state will not be a state that starts dropping Cokes out of the machine, nor will it be a state that starts giving money back, right? So let's just call this the initial state. And that's going to sort of be the power on state of where it is when we first power the thing on. And then the question is, if we're in that initial state, the power on state, what sort of things might happen? Well, you know, some sleepy-eyed student comes up and pushes the button saying, give me a Coke. Should the machine do anything? No. Okay. So if the input is give me a Coke, which I'll just write down as Coke, as the button, the input, then the response should be nil. So right here, do nothing. Chalkboards are great, except they make the lecturer sneeze. Do nothing. Okay? And furthermore, the machine should not suddenly get mad and, you know, start spitting money at the person or anything like that. It should kind of go back to the initial state. Now, what happens if the person, on the other hand, instead of saying, give me a Coke, says, give me my money back? Should it do anything then either? No. So let's go ahead and say that return should basically do the same thing. And notice what I'm doing here. I am putting the input conditions here and the output conditions here. This is in, this is out. Okay. And I'm also drawing a arc which says if I'm in this state and this input occurs, go back to the same state. So I'm both giving a mapping of in to out, which depends on the current state, and I'm also giving an arc which says what transition to make. In other words, I'm saying given input what should the next state be and what should the output be. And what I'm saying with that one there is the output should be nothing, none of these, and the next state should be the same. Okay? Okay, let's handle the other cases. How about nickel? If I put a nickel in, what should I do? Well, if I'm a typical Coke machine at MIT, I swallow the nickel, and I'm still in the initial state. But let's say that we're at Harvard, where the students actually are good at money, and they insist that the Coke machines be fair. Clearly what we want to do is if the nickel input comes in, then we want to remember it. We want to be a different Coke machine than we were before the nickel came in, and we want to change state. And I'm going to label this state, I got 5 cents. And I will remember that I have 5 cents, which is good. Now, do we want to do anything on the outputs? Do we want to give the person a Coke? Do we want to do anything? No. Okay, so we do. That's absolutely right. But in this case, we're assuming that he's only pressed the nickel button here. But if we're in this state and the person presses the return key, like you just said, then what do we want to do? We want to return a nickel and we want to go back to here because he said that. So if they press return as the input, we want to return 0.05 and we want to go back. So again, this is the input condition and this is the output command. That make sense? Good. Okay, what if we were in the initial state and the person put in a dime? We clearly want to remember that, but we don't want to remember it in this state, so we need another state. So if they input a dime, like here, that was one of my inputs, right? Dime. We want to, again, do nothing as an output. But we want to remember it differently, and we put it in this state saying got 10 cents. Good. I think that we've handled all 4 possible button presses that could happen going from this state. Now, if I were really being careful designing this Coke machine, I would actually have to say, what if he presses return and puts in a dime at the same time? Because that's actually a different combination of inputs. Remember, there's 4 bits here, so it's not that there's 4 combinations. There are, in fact, 16 different things. But I'm going to make it, and it actually used to be the case that if you pressed give me a Coke and give me my money back at the same time, and you got the timing just right, the machine would give you both. Okay, it's actually true. Okay, my old thesis advisor at MIT actually taught me how to do that. Those are the good old days. Question authority, right? But I'm going to assume that inside of we're going to put a mutual exclusion circuit. Which is going to stop me from trying to hack with this thing and only allow one of these 4 to be on at any given time. Okay? And that's going to make it easier for me to draw this picture. Because instead of worrying about 16 conditions going out of any given state, I only need to worry about 4. Okay? And that'll just make the class a little bit easier to teach. Now, if I've got 5 cents and the return key goes on, we know to return this. If I've got 10 cents and the return goes on, over here, return, comma, return a dime. Okay? That's good. If you press Coke, nothing should happen. All right? This is Coke. Nothing should happen. And I'm just going to leave it blank. Same thing here, right? If I press the Coke button, nothing should happen. Is there anything else I need to do?
You might want to return the nickel if you press return nickel.
In other words, if I put in a dime and I hit the return key, I want to return a nickel.
But there's not a button.
Oh no, but there's only a button to return everything. Yeah. This is just like those Coke machines with that silver button that's really hard to press down. It kind of tries to unjam the mechanism and stuff. Okay. So what's left to do? Well, Really, if I have 5 cents and I add another 5 cents, I want to go here. So if I have a nickel, again, I do nothing. And in fact, I don't even need to write this down, do I? I can just kind of leave it just like that. And if I'm here and I put in a dime, then what do I want to do? I want to go to a third state. So this one here is dime. Again, I don't do anything. But now I'm in this fourth state, which is I've got 15 cents. And if I've got 10 cents and I get a nickel, then I go here. Okay. And if I've got 10 cents and I put in another dime, then what am I supposed to do? Well, I kind of want to go to here too, but I want to return a nickel. So here's that nice little state, return 0.05, which is actually what the machines do, right? If you put in too much stuff, although maybe they don't do it till you actually push the button, but different machines work differently. But this one, as soon as you put in too much cash, it'll start giving it to you back. Okay, have I handled everything? Out of each one of these states, there needs to be 4 arcs, because I've said there are 4 possible things that we could do. Out of here, there's 1, 2, 3, 4. Out of this one, there's 1, 2, 3, 4. Out of this one, there's 1, 2, 3, 4. So far we're good. We've handled all 4 cases for each of those 3 states. Now finally, we're in this terminal state. The machine's getting all ready to give you Coke. And those of you who use real Coke machines know that the machine starts to buzz when it is in this state. Have you ever heard it? It kind of hums, right? It goes, like it's like, oh boy, I'm getting ready to give you a Coke. You know? I have no idea why it does that. But, anyway, so now what are we waiting for? Well, if the person presses the Coke button, it gives them a Coke. Go back to the initial state. So another big arc over here saying if they press the Coke button, then we want to drop Coke and go back to that state. The return button over here, same sort of deal. Here's return, and we want to give them 15 cents back. Right? Return 15 cents. And what if they put in another nickel? We want to sort of stay there. So here, nickel. We want to return 0.05. And if they put in a dime, we want to stay in this state. Return 10 cents. And there you have a state diagram for a simplified Coke machine. And what it says is that there are 4 states, and that there are 4 inputs, which are mutually exclusive in this case, and 4 different outputs that this thing may have. And what's neat about it is that now we can go ahead and encode this in hardware. Now, how many bits of storage do I need to remember which of those 4 states I'm in? There's 4 possible states, so how many bits do I need? 2, right, because 2 to the 2 is 4. So there are 4 combinations. So I know that I only need 2 bits here and 2 bits here. And this thing will keep track at any given time what the current state is. And if an input comes along that matches the current state, then when the clock goes off, I'll make the transition to the next state. And if the input comes in and I'm in a current state, it will generate an output having to do with whatever I specify over here on these arcs. Let's take a look at what that actually looks like. First of all, before I do that, what are the rules? When you draw state diagrams like this, first of all, the arcs that go out of a state must be mutually exclusive. What does that mean? I cannot draw a state diagram in saying that there are 2 possible arcs that you might want to go towards. If one arc says, if you press return, go this way, and there's another arc that says the same thing, how do you know which one to follow? So they must be mutually exclusive. The arcs out of the state must also be exhaustive. What does that mean? You have to handle all possible inputs that the person might give you. So sometimes, in fact, if you want to just have a arc that says, in all other cases, do this, you can use the symbol star, and that's sort of a nomenclature thing. And so one of the things that I could have done here, instead of writing all this stuff out, is I could have just said, in all other cases, stay in the same state. All other cases, stay in the same state. And this is very common, that you want to sort of do nothing and stay in the, oh, except these, I can't do that, right, because I'm actually taking an action, and the action is specific for this or for that. So I'm going to leave those be. But here I say in all other cases, just stay in the same state. And I could even write comma, do nothing, okay, meaning none of the outputs. So we have to be exhaustive. The starting state should be defined when you first power the machine on. We did that on the left-hand side. All possible states should be defined with transitions to the starting state. Sometimes, for instance, if it turned out that our Coke machine only needed 3 states, and we still used 2 bits in order to encode it with this number of wires, there would be a 4th state that we didn't draw on the picture. And the trouble is that sometimes machines have states for which there is no encoding saying go back to the starting state. And the machine sort of gets wedged in this state, and you have to push the reset button to get it back down to the first state. So a good habit to get into is, first of all, making sure that you've considered all the possibilities of what the state variables might be. Because when you power up the machine, sometimes it's unclear what the state, memory state may be at when it first turns on. And as we said before, S state requires 2 different state variables. That's totally wrong. What is wrong about that? So S state variables have 2 states, is what it should have said. Okay. S state velocity. Quite that. It's the ceiling velocity, right? 1. Sir. Okay. Here's what the architecture looks like. We saw that before. A little bit about the different kinds of machines that we have. There's actually 2 kinds. One's called a Mealy machine, and one's called a Moore machine. These are the 2 fellows back in the 1940s who thought of these things. And what we've been talking about here is called a Mealy machine. And what that means is that the output is dependent, I think you can see this between the blue and the gray. The output is dependent on both the input and the current state. And the next state is dependent on both the input and the current state. And the way you draw the diagram is the way that we have drawn it here, with input, comma, output on each one of the labels for the arcs. And then something describing what the different states are inside of the circles for each one of the states. An alternative nomenclature called a Moore machine, which is a little bit more restrictive, and that says that the output is only dependent on the current state and is not dependent on the current state and the input. And you'll see this some of the time in the future, so I just wanted to make it clear how this thing works. Here, the inputs are on the arcs, the way that we did it, but the outputs are not on the arcs. Instead, the outputs are inside of the states themselves, because again, it's saying the output depends only on the current state. So when you have a label for this is the current state S1, comma, and whenever we're in that state, the output is O1, such and such, okay? So it just says the output only depends on the state, not on the state plus the input, which is going to give us this arc. Here is the truth table that you might have, for instance, and the question is this a Mealy machine or a Moore machine? Does the output depend on the current state or the current state and the input? So here we have bits of current state. Here's the next one. Does the output depend on just the current state or the current state and the input? Well, from what we see so far, it seems to depend only on the current state, from what we see in this picture so far. Okay.
So it ought to be a Moore machine.
Oh, whoops. You're right. You're absolutely right. So this is wrong too. I'm sorry. Huh. Moore machine. Wow, there's several hundred MIT students that got this wrong last term. Yikes. We can draw these state machines a little bit differently too. One of the nice things to do is to try to separate out the function that's in blue from the function that's in gray and say that in fact, we take this over here, put it in two sections and such. And this, if you look at it, it's actually exactly the same thing. We have combination logic. Two outputs here. And next state that's going to go into it. And then we have separate combinational logic on the output, which takes Q and generates it out. And the difference between a Moore machine, which is this type over here, and a Newton machine, arrow here. Okay, now, enough about sort of an introduction to FSMs. What I want to talk about now is why do we need that register down at the bottom at all? In other words, why can't we just take and hook it around here to the current state? So in order to do this, I have a wonderful little experiment that I do with some students. So what I want to do, and I'm going to do sort of a shortened version of it. Let's take the students sort of, let's see, 2, 4, you guys, and you guys too. I think we may have one extra, but come here and form 2 rows of 4 each. Okay? I'm going to make a state machine out of you. Okay. And what I want you to do is, yeah, there isn't much space here. Okay.
Standing up?
Yes.
I'll join if you don't want to. Okay, go ahead.
Okay, good. Now, what I want you guys to do, no. You are actually going to both have lines, and you're going to face the front because you're going to draw on the board. And you guys get a piece of chalk and one of the erasers over there. And give me one of the erasers here. I guess we could use this one here. So you get this and you get that. And here's what I want you to do. Okay, and I'll put this up on the board. Okay. You're supposed to wait your turn. Okay. And then you're supposed to look at the 2 numbers on the board. Now you see 2 1s. Now you're supposed to immediately erase the number that's in front of you. And then you're supposed to, in your head, add the 2 numbers and put the sum on the board. And then walk to the back of the line. Okay? Now, there will be a temptation amongst the 2 groups to synchronize with each other so that you're both going at the same time. Now, what should these numbers be? 1 plus 1 is 2. 2 plus 2 is 4. 4 plus 4, 8, 16, 32. So it should be the powers of 2, right, is what these guys should do. Except that if they don't synchronize with each other, which I don't want you to do, just go as fast as you can, but don't synchronize. If you need to wait for a number to show up, then do that. But otherwise, don't try to sync up, okay? Are you ready? Everybody get it? Set?
Well, you need the 2, don't we need 2 1s to start with?
These are the 2 1s.
Oh, sorry.
Okay, that is okay. It's okay. You have a sideways view there. You couldn't quite see it. Okay, go. Ah, good. You don't need, there's actually no reason to go super fast. You can just kind of go at whatever rate you want to go to.
Yeah, but
You should add the numbers and don't try and cheat. Don't look ahead or anything. Just add your number with the other number. And you guys go as fast as you can. See, people always tend to lock up. They always are nice. They wait for each other. Oh, good. Okay, so now the numbers are getting big, and I think that we can actually stop now. So what obviously happened is that we did not get the powers of 2. Okay, wait, you aren't done yet, guys. Come back. Now we're going to do it slightly differently. I'm going to do it a little. Do you still have chalk? You have chalk there? Do you guys still have chalk?
No, we
Okay, let's get it purple here. Okay, let's put 2 1s back on the board. Okay, and this time I want you to wait for me to say go each time. In other words, I'm going to be the gate that enables the next step in this FSM. So don't Each person don't go till I say go. Go. Now you guys wait. Okay, we all settle down? Okay, go. Now I wait till the logic settles down. Ready? Go. And obviously, okay. And of course what happens when I do this at MIT is that the students now write stupid numbers up on the board that have nothing at all to do. Go. Okay, that is good. Okay, you guys are much nicer than my usual students. They who always manage to making the other case work and this case not work. But you understand what just happened here. Without a synchronizing delay, without me saying wait, okay, now do it. And then wait, okay, now do it. Okay. This system gets out of control and it races ahead and different parts of it go faster and different parts of it go slower, and it's very difficult to control the speed of the feedback so that all parts of the feedback operate at the same time. And so the key is delay. We put a gate there, we say don't do it yet, okay, now go, and then you close the gate. And then you wait, okay, go, close the gate. And that's why you need that element down in the bottom to synchronize the delay. So effectively, we're going to talk about why we need register here. And this is going to be one of those possible things that we use, which is the register that we've seen. And I'm going to introduce a new word for this. This is actually called a flip-flop, okay? And the reason it's called a flip-flop is that when these devices were first invented, the idea was that it can be, if it only holds a single bit, it can store one of two states, either a 0 or a 1. And when you clock it, it can flip into one state or flop into the other state. So a kind of nice word for it is a flip-flop, okay? Sort of like the sandals you wear on the beach, right? Okay, now, how does it work? Well, we talked about this before. If D is going to be the next state, then when the clock goes from low to high, Q changes from whatever old current state it had to whatever the next state is over here. Place. The thing we're going to talk about for the rest of the lecture today, however, is exactly how much time it takes. And we're going to talk about some of the details of the timing, which to some extent are going to make your head swim. Okay, but don't worry, we're going to do it again in the next class, and it'll become a little bit more clear.
In that diagram,
Yes.
what's the meaning of
Of these hash bars. That's exactly what we're going to talk about now. Okay? Now, logic levels cannot instantaneously change from old to new. When we were writing numbers on the board, what happened? The first thing that happened is that we needed to erase the old one. And for a while, the board was blank. It had no data on it at all. And then the new number got written down. What's happening here is that this is the old value of the current state. It gets erased, and we can't read what it is, and then the new value is written. Okay? And this is exactly the way that registers always work. So, what we say in the notes, using it, is after the clock goes off, there is a short amount of time which is called go, and when you guys erase the numbers from the board. Because if you remember, that's what I did. I said go, and then the old numbers were still on the board, and then the erasers came out, and then the number was gone. Thing gets garbage also. Well, right here, this value Q, the current state, switched from its old value to erased. And then finally the new value popped up. Well, if you think about it, that signal saying old value, garbage, and new value went into this logic here as well, into the head of the next person in line. And the logic, just like people, cannot compute instantaneously. It has some delay as well. And so that signal was delayed, saying what the next state is, and that's exactly what we're here. Time is going by on the x-axis, and so 2 goes from having its old value being erased. A short time later, D goes from the next state to being some intermediate thing that we're not sure of. And then finally, when this thing settles on what the next state is going to be, a short time after that, that combination of logic produces the next state. So let me write this on the board and draw this out in a sort of on the blackboard, because I know this is kind of confusing. And again, don't worry if you don't get it right now, because we're going to go over it and over it and over it. So now let's see, this is being drawn as D and Q. I'm going to draw this just a little differently this time, just to make it maybe a little more clear. I'm going to say, here's the combinational logic, and here is the other half of the combinational logic. In other words, this thing is a loop, but I'll unwrap it to make it a little more clear. And so this edge here is the same as that edge there. And here's the clock that comes out here. Okay? So now let me draw a little timing diagram down at the bottom. Here's the clock, and here is D, and here's Q. So the clock goes from low to high, like so. Okay? And I'm assuming that the D value is going to be stable around that time when the clock goes from low to high. It will either be a high or a low, and there can be many bits here. So all I mean is that the bits are all set up. The Q, after the clock goes from low to high, a short time after that, what happens first? The first thing that happens is the Q, which also used to be either a high or a low, a short time afterwards, Q goes from that high or low value to an intermediate value, which we don't know. In other words, the old value of the current state is erased from the board. And this time between when the clock goes from low to high and when Q starts to change is called the contamination delay. This time here. How long does it take to contaminate the signal between when the clock goes off and the signal gets messed up?
Is that the way the length of the arrow on the right side?
The arrow that I'm making here, or do you mean this arrow? No. It has nothing to do with how long this wire is, okay? What it is inside of this box, there is a process which takes place. I'm assuming the wire is very short.
Okay.
There is a process which takes place that always, when this clock goes off and it says take the picture, it's like a Polaroid camera, right? You take the picture and first you get out this thing that's white, right? A short time after the trigger goes off. And then after a while, it becomes clear what the picture is. Okay, so this is sort of the developing time for the picture. The time and then put the new one on. And during that time, the board had nothing on it. And during this time, output value. After that, then the value finally settles down into a snapshot of whatever D was when the clock went from low to high. So this value has its picture taken and becomes what Q is over there. And what we're going to talk about for the rest of the class today are the specifics of the timing of how these pictures are taken. The shutter is snapped. For a short time after the shutter is snapped, the old image is still there. It takes time for the logic inside of here to say, oh my God, the clock went off. Okay? A short time after the clock goes off, it says, okay, I've got to change the picture from the old picture to the new picture. So that time is called the contamination delay. Then it takes time to do and so the time from the clock going from here to here is called the contamination delay. It's called the propagation. propagation delay, both of these, yes, they both start at the edge of the clock tick. Here's a way to remember this, okay? The contamination delay, which is actually usually quite short, is the time to get pregnant, okay? This is, I'm serious, okay? This time here is the 9 months, okay? Which is longer, usually. And the propagation delay is actually the time from when you want to have the kid to when the kid pops out, okay? So, you know, and if you can't remember it with that trick, there's no hope at all, okay? But that's basically how the thing works, okay? Because, again, the circuits have no foreknowledge of when the clock is going to take place. And so it takes them time between when the clock goes off to begin to make the change. Then it takes some time for the change to take place, and then the change is done. And if you think about it, there could be no other way that it could work. Okay. Now, after the output Q gets contaminated, that contamination begins to filter through the combinational logic over here. And so a delay through here, which is actually the contamination delay of the combinational logic, is the time it takes for the contamination to hit here. And so this also gets contaminated a short time after that. And so let me write that kind of like this. And so at the time from here to here, this is the contamination delay and propagation delay of the flip-flop. There's another time here, which is and I'm just going to write this now with the actual symbols that we're going to use, TCD, for time contamination delay of the combinational logic. TCD of CL, between when the input to the combinational logic is contaminated, which is this thing here, and the output to the combinational logic begins to be contaminated as well. And then, after that, finally, this settles down. And notice, this is the next state. This was the current state. And what this did is it made the next state, made the current state equal to the next state. So therefore, this thing that's being figured out is the next state. Okay? And so how long that takes is from the time that the input to the combinational logic over here is good until the output is good, and that's the propagation delay of the combinational logic. Okay.
T with a sub with a sub?
It's T with a sub with a sub, and I know that it's hard to see, but it's T sub PD sub CL, and this, another way of writing this here, is T sub CD of FF. And here, this is propagation delay of the flip-flop and the contamination delay. Contamination delay is the time from when the input changes to when the output starts to change. And then the propagation delay is the time from when the input is all done to when the output is all done. And in the case of a flip-flop, we measure both of those from the clock edge. And in the case of the combinational logic over here, we measure it from when the input begins to be contaminated. So let me see if I can get this exactly right. Current state is over here. TCD of CL happens between here and here. TPD of CL happens between here and here. You don't need any of this stuff I just gave out. Have you guys gotten that yet? Did not see this? This is all. And the problem set will include some good definitions of this stuff, so it'll become clear. And again, this is the first time I'm showing it to you, so don't. The students at MIT have a. We're going to go over it and over it and over it and over it. But I wanted to get started anyway. Okay. Yeah.
Does this system not potentially make something go horribly wrong inside the combination logic? When the garbage value in Q...
That's a great question. In other words, if you're looking at the board and you're trying to add, and all of a sudden the number disappears, why does smoke not come out of your ears during that time, right?
Or, like, if accidentally the value that came out was the value that said shut my machine down.
Right. Well, but the combinational logic doesn't have the power to do that. All it has the power to do is to come out with an output. And so when there's contamination, when there's garbage, so what you're asking is during this time, combinational logic. Here's the Q value. During this time, there's garbage going into the CL. Why does the CL not go nuts and overheat and do bad things? And the answer is that the combinational logic is built in such a way that it can handle it. Right? If the input is good, it generates good output. If the input is good over here, it generates good output over here. And if the input is garbage, it generates garbage. Okay? And that's just the way it works.
Because it's good.
Wait, we're not going to clock it until sometime over here. We clocked it here when the output of combinational logic was good. And we're not going to clock it again until over here, after all the garbage has passed through.
And if we did clock it when the garbage was going
Then the machine would jump into a random state, and you'd get the blue screen of death, and Windows would crash and all that. We're going to talk a lot about how to prevent that from happening.
make another feature.
Yet another feature. The very next thing that we're going to talk about. How do we decide when it's safe to run that clock back up again? Notice that that clock went from low to high when the next state was nice and stable. Now we want it to go from low to high again when the next state is nice and stable. And how do we do that? Well,
These times depend on the circuitry or on other factors. I mean, would like a high signal travel through faster than
that's
low
a
signal?
great question. In fact, highs and lows do travel through at different rates. And when the circuit's hot, it works a little differently than when it's cold. Okay, it's usually a little faster when it's cold than when it's hot. Is how it works. The length of the wire matters a great deal. And so, in fact, it turns out that the numbers that are given in the books that specify what the contamination delays are and what the propagation delays are worst case numbers. And so the contamination delay, which says how soon from garbage in to garbage out, is always given as a minimum number. How soon could this happen? And the propagation number, which is how long does it take between good data going in and good data going out, is given as a maximum number. At most, how much could this take? And it's given over the entire range of temperatures and data values. Okay, so for any data value and any temperature within range from minus 20 degrees C to plus 100 degrees C or something like that. And it turns out that there are different specs depending if you build parts for the military, for the home. There are different types of specs for those things. These are always given in terms of worst case. Okay?
And the clocks are adjusted accordingly.
And when you design the system, you decide how to clock it exactly by that. So when you buy a chip, for instance, and you overclock it, some of you have heard about doing that, you turn the clock up. What you're doing is you're saying, well, you know, this was designed to run up to 75 C, let's say, if it was meant for the home, which is pretty darn hot, but that's on the surface of the die, of the chip. I'm going to assume that it's going to be cooler than that, and I'll clock it a little faster. And the answer is, well, probably if you allowed that thing to get real hot, it would then fail. Okay, so that's absolutely right. Okay, what's going on here? It turns out that, yes?
Don't you have the same problem with the clock, with knowing when the clock fires?
Absolutely right, and we're going to talk about that too. The clock may fire at the wrong time too. And in fact, the oscillator that generates the clock is not perfect. And there may be some jitter. The amount of time it allows from one clock to the next may be somewhat uncertain. And in fact, the oscillators that you buy have specs on them by how much the clock may be off. The clock may run fast, the clock may run slow. And actually, the clock itself, as it makes its transition from a logic low to a logic high, takes a little bit of time. And during that time, you're uncertain what the clock is. And we're going to talk about that too. Okay? So everything is uncertain, but luckily there are bounds on all of these things. And so you're going to get into how all this stuff works. But let's first of all talk about this business of taking a picture of the data. So it's really great because the questions have led directly to this thing. When can I next make this clock go from low to high? I know I have to wait till the next state comes out here, because that's coming in on D, and that's the next time that I can tell this thing, take a picture of the next state. So I basically want to, I can drop this clock down whenever I want because it doesn't listen to that, but when's the next time that I can make this clock go off again? And I know I have to wait until this thing comes in, but can I clock it right here, right when the next state first gets there? Or should I wait a little while for things to settle down like I did here before I say go? And you remember I waited till everybody sort of settled down, right, and everybody was happy. And I said, okay, go. And I in my head was doing that. Well, it turns out that in designing these things, there is a technique that we use and a set of specifications around the clock edge of these flip-flops, of these registers, with a time of quiescence, a time when the D input, the data input, is supposed to stay stable. And that is called the setup time and the hold time. And going back to our old model of the flip-flop or the register as a camera, what we're really saying is hold still, I'm going to take your picture, click, and then you wait a little bit and say, okay, you can move now. Okay? Because if we take a picture when this thing is in the middle, when this thing hasn't settled down yet, the picture might be fuzzy, and we may get the wrong data value. And in fact, in the next lecture, we're going to talk about all about what happens when we're forced to take a picture of an object that is moving, when we're forced to try to sample data that may be changing at the same time. But the first rule is going to be don't do it. Wait for the data to settle down, take the picture, wait a little bit longer, that's the hold time, and then let the data change again. And so we're going to surround these clocks with a time of quiescence, set up and hold, T sub S and T sub H. And that's exactly what's going to determine how fast we can clock things. Because after this thing settles down, how long do we have to wait before we can fire the clock? T sub S, right? So the time from here to here, at minimum, will be T sub S. And then hopefully the time from here to here, it will still be the case that it's T sub H.
I'm not clear exactly. The T sub H is the time the data should hold, but how are we?
How are we to ensure that? That's right. That's hard to do. Because varying the period of the clock doesn't seem to change that, does it?
Isn't it the amount of time that it's going to take to get through the logic circuit?
Absolutely right.
Causing that?
Absolutely right. That's extremely good to see. Because, in fact, when this thing goes off, a contamination time later, this thing turns to garbage, right? The time to get pregnant. I actually have never used that joke, so in the future at MIT I'll use that joke, although I might get kicked out. Yeah. Anyway, and then a contamination delay of the logic after that, this goes bad. And we just said that the rule is that we have to allow this to stay stable, because this is what is being sampled by the clock. This time here must be greater than the hold time. We want this data to be held for at least T sub H. So let's say the T sub H goes out to here. If that's the case, everything's fine. This data was held for that long because the contamination couldn't race around the loop fast enough to contaminate the signal that we were trying to take a picture of. On the other hand, if the spec for T sub H is this big, then we failed. And the system can never work, no matter how slowly we clock it. So now let's talk about that.
So T sub H we want to be smaller.
We would love for T sub H to be as small as it possibly could. We would also love for T sub S to be small, because that means we could clock it faster. But for it to work at all, T sub H has to be less than the sum of the contamination delays going around the loop. Okay, I'm actually going to skip this section in the notes here on the transparent latch, okay? And instead I'm going to do this one here. And that's in the interest of time, and we're going to get into the transparent latch, probably not the next lecture, but the one afterwards. So let's go to page 21 here. The clock goes off, and a time between time 1 and time 3 after that is the propagation time Okay. Unfortunately, I have to tell you one other thing. which is the following. TPD min is equal to TCL. TPD max is equal to TPD. So it turns out that in this subject, which we've taught at MIT for a long, long time, we use this term contamination delay, T sub C D, is what I mean, contamination delay, and we use the word propagation delay to mean those two things that we talked about. The industry actually uses slightly different terms. The minimum propagation delay and the maximum propagation delay. So the minimum propagation delay is the time between when an input goes off and the output no longer has the old value. The minimum time to propagate from here to here. And the maximum propagation delay is the time from when the input goes off till when the output is good with the next new value. So you're going to see terminology, unfortunately, here in the slides, and I don't want you to get mixed up, between TPD min and TCD and TPD max and TPD. What I meant in the pictures here is actually the same as what we showed here. So let's take a look at what this shows here. The time from time 1 to time 3 is from time 1 to time 4 is TPD max. The logic itself, here's the logic, is from time 3 when the input to time 5 when the logic produces a contaminated output, and that is TPD min of the logic. And TPD max is the time from when this output is good over here, time sub 4, until this output is good over here, and that's time sub 6. So the time between 4 and 6. So what do we have to ensure in order for this thing to work? Some of the contamination time. Is the logic, the time for the flip-flop between the clock and the Q here, and we also have to ensure that that is greater than the time of the flip-flop. So what are we saying? We're saying that we want to make sure that if this is the input to the flip-flop, that this is not contaminated before that hold time, T sub H, has expired. All right, second constraint is that the clock period has to be more than the sum of the propagation. In other words, the clock goes off. We have to wait for the propagation time from the clock to the Q output of this thing, between when the clock goes off until when this is good. Then we have to wait for the propagation delay of the combinational logic, between when this becomes good and this becomes good over here. And then we have to wait, once we've arrived back here again, we have to set up for the setup time. And only after those 3 periods of time have passed can we fire off the clock a second time. And that's exactly what we saw over here. We have to wait for the TPD of the first chunk, TPD of the second chunk, plus the clock a second time. And that will inform how fast. Wait for the data to go from here to here, wait for the data to go from here, around to here, and then stay here for T sub S, and then you can clock this a second time. That was the constraint on the clock period. Again, the constraint on the hold time is make sure that the data doesn't race around here, the contamination doesn't race around the loop faster than the amount of time we expect this to be held after the clock goes off. And that says that the sum of the contamination delays, or another way of saying it is the sum of the minimum propagation times around the loop, has to be more than the hold time. All righty.
So all these times kind of the same order on amplitude, or is like some something?
Well, it turns out when you design flip-flops, you often set the hold time to be very small. So you set T sub H, in some cases, to be 0. And the setup time is usually the bigger time of the two of those. The propagation times tend to be bigger than the contamination times because, you know, the pregnancy takes longer than getting pregnant, right? So, and you have to get pregnant first, right? And you measure it all from the same time. So that's also true too. Okay. Let's take a look at the final question which was asked, which was clock skew. Okay. We've shown a system where all the registers are on the bottom at the same time. But is that actually the case? The clock isn't perfect. The wires are not perfect. The parts inside of the register are not perfect when they perceive the clock on the input. What would happen in a system if certain parts were clocked before others? In other words, let's do the, let's not actually do it, but in our minds, let's do the experiment where instead of me telling each one of the folks here, go, and they both went, there was actually some skew between their perception of when I said go. In other words, the guys on the right had a long tube going to my mouth, and the guys on the left had a short tube. And I say go. And the one on the left, 3 seconds later, the one on the right goes. Would the numbers still go up in sync with each other the right way? No. Well, let's assume they're both seeing the numbers perfectly. The last time they looked at it is actually, even though they until I say go. In trouble. The clock skew, the fact that the clock doesn't get all the parts of the system at the same time, is going to make this timing more difficult to get. And so, in fact, you need to take into account this clock skew as well. The clock skew is difficult to do. In general, the contamination delays have to be greater than the hold time. Very bad could happen. Let's say that we clock this one over on the left. Okay? We go bang. And the contamination starts to go out here. Then the contamination starts to go out here. And then we go and the input will be contaminated before the whole time. In general, what you do with these skew times is you figure out what's the maximum skew in between the two parts, and you set up the constraint so that the margin is greater than the skew time. And if this is true, then you can be sure that everything is fine. In other words, if the difference between the two clocks is bounded by some number, so that the amount of safety margin that you have between the margin. You also add that margin as well to the amount of time in between the clocks that you a little bit of skew between the two people that I was saying go to. I'd shift this clock out a little bit more to make sure that all parts of the system were settled down before I said go. Okay. Now, let's just, in the last few minutes here, handle a few things having to do specifically with the Coke machine. In general, logic that you design, AND gates and OR gates and things like that, itself has a contamination delay. And you asked the question, if this during the time that this is contaminated, all bets are off as to what this output is going to be. Now that's no big deal if there's no output, because like we just said, garbage goes around. But what if this output goes to the little mechanisms in the machine saying drop a Coke? Or even worse, drop 5 cents and drop 10 cents. Or if this is a thing for zapping, going up. Because of answer is that we can solve that problem by putting another register over here. And this register is garbage. And this output will not get changed when this thing is suddenly switched. The only time that this is going to get changed is right after the clock goes off one. Except that flip-flops have a very nice characteristic. And the characteristic is as follows. If the output was 0 before the clock goes off, and the output is going to be 0 after the clock goes off, in other words, if the new picture is the same as the old picture, then it turns out that during the contamination time, a flip-flop actually holds the 0 as well. Okay? In other words, if I take a picture with the camera, right, and then I take another one and the picture is exactly the same, during that time where it's developing, it still has the same picture. And so how this thing solves the problem is if the old output had a certain value and then got contaminated and then got the same old value on it again, then when we take the picture of the new value that's coming out here, if it's the same as the old one, the output here will never change and you won't see the glitch at all. It's only when it's changing from one value to the other that it goes through this intermediate time where the picture is developing on the output that we actually see trash there. And so this kind of a circuit here can actually de-glitch the output and ensure that it doesn't drop a code by accident. Okay? And that's used inside of these machines all of the time.
If you do change state, though, you do get a short period of trash.
You do get a short period of trash. And we're going to talk about how to encode the data here so that you don't misinterpret the trash as the wrong thing. I know this has been sort of a whirlwind tour here of how to do timing on your system. Do not worry. We're going to do this a lot more, okay? And it'll become really much more clear. But since this is being done in a sort of a top-down way, you sort of had to see it at first. And so that's kind of been why this just kind of goes over what it is that we did, okay? And it'll become a lot more clear, particularly in the problem sets that you're going to do next week, just exactly how this stuff works. And then we're going to talk about how to actually build the inside of this register. And what's really cool is you're going to see where the timing delays actually come from. And that's going to help you understand it even more. Okay? Thanks. And I'm sorry if I've mixed you up, but it had to happen.